So we're very pleased to have our next speaker, Professor Michael Drmota from Vienna, and he's going to be talking about pattern counts in random planar maps.
So thank you very much that I can give this talk here. So the topic is on random planar maps, which is also a random network or a random graph, as you will see. And but the methods that I will be using are maybe not the mainstream of this meeting here. It will be more combinatorial and analytic. But what is the general problem that I'm interested here and also in different contexts is the following. It's quite a simple one, that you have, say, a local function on a graph around a vertex. A typical, the easiest example is that you just look if a vertex has some given degree. So degree 3, for example, and you count the number of vertices of degree 3, or you just take the sum of this functional over all vertices. And it's under very mild conditions. For example, if you have a Benjamin-Schramm limit and it's clear that this sum, the expected value of this sum is approximately linear. But the problem that I want to discuss here is what can you say about the limiting distribution of this sum? Well, of course, you expect a central limit theorem, and this is actually the right answer. But it turns out that, in particular in this situation, the problem is not easy to handle. So what is a planar map? So a planar map is just a planar graph embedded into the plane or sphere together with its embedding. So it's slightly different. The model is slightly different from just saying that it's a planar graph. You can also think of just n-gons that you glue together. So it's a map of countries, for example. And in the most general case is that you allow multiple edges and loops. And of course, if you put this loop to a different phase, then it's a different map. And it's also useful and common to introduce a so-called root edge, which is directed in order to, say, destroy symmetries and also to have a way of reproducing it in some way recursively. So because if you put away the root edge, it's a canonical edge that you can take away, then you get a smaller map and so on and so forth, so you have a recursive relation to construct maps and also to count these maps. And this goes to the famous formula by Tat, who discussed many questions on maps, planar maps, and particularly he counted planar maps, and he got a very nice formula for the number of rooted planar maps with n edges. It's also interesting to see the asymptotics of this number, because it's not only it's exponential, 12 to the n, but the interesting fact is this n to minus 5 over 2, this sub-exponential growth rate, this seems to be universal for a big number of classes of planar maps. And the method that is used to prove this is by using generating functions, a power series, where these numbers mn are the coefficients. And it turns out that this generating function is actually an algebraic function and very explicit. And I will come back how this relation or this explicit formula can be obtained. By the way, generating function will play a very prominent role in this talk, and because it's very combinatorial, the method that I'm using, and so generating function will be used all over the time. I just want to mention quickly that the method to get this result is by introducing a so-called catalytic variable, so a variable that is not really used, but is not needed, but is used to get some recursive relation, because if you don't use it, then you don't get it that directly. There are other methods to do, but what is the method? I already explained that the method is to remove the root edge. And there are two cases. Either the root edge disconnects the map, so it's a bridge, then you get just two maps, and this is the square, or it does not disconnect the map, then you get the part that is related to this, and here it is catalytic variable that takes into account the valency of the outer phase is needed, and so you get a relation for this function with this catalytic variable that appears sometimes, and sometimes is set to 1. And there is a method that is called quadratic method, or it's a generalization of this of the kernel method to get solve this kind of equation and to get this explicit formula for the generating function. From this explicit formula, you can get also this explicit formula that for the number of maps. Okay. This is a picture how a big planar map looks like. So it's this, and it seems that there is a kind of random surface that is a scaling limit of this random planar map, and this is actually true not only for the general planar maps. There are many different classes of planar maps that you can consider, quadratic bipartite maps, and so on. And in several of these cases, it's already proved that there is a scaling limit, because if you scale by the 4th root of n, the distances, then this planar map converges in the proper sense to this random surface S. So this is a very interesting object, and it also shows that these objects are of interest. For example, it's house of dimension 4 and so on. And so this has studied a lot. But there is a second point of view that will be more important for this talk, namely the local limit or the local structure. So what does it mean that it has a local limit? So you look, for example, to the vicinity of the root or the root edge, and it turns out that if you look to the vicinity, so the vicinity of some diameter or distance, if this stabilizes probabilistically, then it's called a local limit. That has been proved by several authors. And it's also possible to make out of this local limit around the root edge a general Benjamin-Schramm limit, so that you consider a random chosen vertex and the vicinity of this random chosen vertex. And this also stabilizes. This was observed together with Benedict here in the audience some years ago. This is it's a very easy corollary, but it also shows that random planar maps have a Benjamin-Schramm limit. Of course, we rely on the previous work. And from this, you can get very simple, easy corollaries, as I've mentioned in the first slide. So, but now I come to the main topic of this talk, to pattern of a planar map. What is a pattern? So a pattern is some local given structure. For example, here you have two quadrant configurations that are joined by an edge or two edges. So this is a pattern. So a pattern is, of course, again, a planar map, and it appears in some sense as a submap. And the simplest pattern that you can think of is, of course, just a face. So you don't have these edges here. You just have a face of given valency, a triangle or a quadrangle or whatever. So this is the simplest pattern. And of course, this is a local structure, and you can, if you dualize, then this is the phase valency gets just the degree of the corresponding vertex. So, but for planar maps, it's more common to use phases and phase valences. So, and from this property, we directly get that the number of, the expected number of occurrences of a given pattern, any pattern is asymptotically linear. And it turned out to be a quite difficult problem to prove a central limit theorem for these pattern counts. And the purpose of this talk is to give you a kind of overview of some methods that we have been using to prove the central limit theorem. And our first results only worked for phase count, so for the number of triangles and so on that appear. So for general pattern, there was a big difficulty that we had to face with, and finally I will show you a method where we could prove, at least for some classes of pattern, a central limit theorem. Here is, in some sense, the story. So there was a first paper on a central limit theorem by Garn and Wormwold in 2004, which introduced the method of moments that we also have been using later. It's a very specific situation. So then the first result, but just for phases of given degree, together with Costa Panagite and two other courses in 2013 and 19. And the first real pattern was then studied with a PhD student of mine, Guanrui Ru, in 2018, just a double triangle. Double triangle is just an edge attached with two triangles, which is a very simple pattern, maybe the most simple pattern you can think of. And even this was not easy to obtain. But more recently this year, we put a manuscript to the archive together with Eva Maria Heinzl and Nick Wormwold, where we could get a central limit theorem for pattern with a simple boundary. And the methods that we have been using are a bijective method, which is quite strong in the context of planar maps, because there are bijection to tree-like structures, and tree-like structures are much more easy to handle. Secondly, the quadratic method that I already mentioned before, where you introduce a catalytic variable to a generating function, and then you try to get relations for these generating functions by doing a kind of recursive method by removing the root edge and see what the result is. And finally, together with Nick Wormwold and Eva Maria Heinzl, we used a method of moments to get the most general result. So, but before I start with the methods, I want to recall some facts that can be used to prove a central limit theorem with the help of generating functions. Of course, we are using some probability here, namely weak convergence. Weak convergence can be checked with the help of characteristic functions, and characteristic functions are with respect to a small change of variables, is just the probability generating function is you use for W the exponential function, you get the characteristic function. So the probability generating function, the expected value of W to the xn, well, is closely related to the characteristic function. And there is a very simple but powerful theorem that is called quasi-power theorem, that if the probability generating function behaves almost like a power in n, then you get a central limit theorem. So the proof is very simple in the simplest form. If you want to get more moments and so on, or local results, it's more difficult. But from this easy property that the probability generating function behaves almost like a power, then you get directly a central limit theorem. But this probability generating function is closely related to generating functions of your objects. For example, if you have some objects, and Cn is the number of objects of size n, you consider the generating functions here, and you also consider some parameter, for example, the number of triangles or whatever, then you have also a more specific number, C and K, the number of objects where this parameter has value K. So if you have, for example, maps of size n with K triangles. And what you are using then is a very probabilistic, very combinatorial notion of probability, that you assume that every map of size n is equally likely, and then the probability distribution for your random variable is just the fraction C and K divided by Cn. And in this context, the probability generating function of your random variable is then just the ratio of two coefficients. So this notion just takes out the nth coefficients of this generating function. So this is just the ratio of the nth coefficients of CW and of C1. So you just have to get out the nth coefficient out of a generating function. And I'll come back to that. So with if you have a generating function of your double generating function of your parameter, then you can get out the probability generating function, and if it behaves like a power, for example, you get a central limit theorem. But there is a second method that I want to use or want to recall here is this method by Gar and Wormold that they have used in 2004 for this result. And this has been not that much used, only recently, also by Luc Devroy and Svante Jansen and others. But this is not that well used so far. Namely, that you consider factorial moments. So factorial moments are just the expected value of x times x minus 1 times x minus 2 and so on, up to some factor. So this is the rth factorial moment. But you're not interested in these factorial moments where r equals 2 or 3, but if r is really big compared or goes to infinity with n, so you need some asymptotic behavior of these factorial moments. If r is not fixed but varies in n, and so you get the rth power of the first moment times a factor of this form. And if this is satisfied, you also get a central limit theorem. This looks quite artificial, but it's also a quite powerful theorem. And how can you check this kind of asymptotics? And it turns out that with this quasi-power condition checks this condition. So if you have this quasi-power condition, then you have this condition and, of course, a central limit theorem. But this is nothing new. If we go back, so if we have this quasi-power situation, then we get a central limit theorem. But if we have these factorial moments, then we also get a central limit theorem, but we also have this implication. So it seems that this is not really necessary, but we will see later that we can use that. And why can we use that? Because these factorial moments also have a combinatorial interpretation in this context. So there is a combinatorial interpretation. It's just a very simple thing. You just translate what is written here. So this is the formula for the factorial moments, and you can rephrase this as the number of objects of size n where are different appearances of this parameter. So for example, r appearance of a triangle are marked, and then you divide just by the total number of objects. So you mark r appearances of your object, your parameter, and you count the number of objects with these marks. and divide by the number of total objects, then you also get this factorial moment. So there is a combinatorial interpretation of that. But now, how can you check this quasi-power condition? And there is a very simple observation, actually. For example, if your generating function has a singularity that looks for it as a square root singularity, but it could be also some other, but square root singularities appear quite often, but that moves, that the singularity moves in terms of the second variable. So you have a moving singularity. Then, by extracting the nth coefficient, that this is not, well, with some easy technical conditions, this square root singularity directly translates into this asymptotics of the nth coefficient. And if now you divide these nth coefficients for CCW and CC1 as before to get the probability generating function, you see directly that you have a quasi-power situation. So this means that if you have this square root singularity, then you get the quasi-power situation and the central limit theorem. But how can you get this square root singularity? And there is another, say, folklore lemma by Bender and so on, saying that if you have a functional equation with some properties of your generating function, then you always get a square singularity. You just have to look at some point where you have a quadratic branch point, so where this functional equation gets singular, then you get a square root singularity. And of course, this also holds if you have a generating function in two variables, then you get exactly this situation. So if you have a functional equation, then you get this square root singularity, or you make it directly. If you have just a functional equation for your object plus some conditions, you get the central limit theorem. So this collects some basic facts on the use of generating functions in order to prove a central limit theorem. So the short story is if you have a functional equation, you get a central limit theorem. But there is also some more structure here, and we will use that also. So now here's the first methods that I want to present to you out of three. So the first one is this bijective method that I mentioned before, that planar maps have a very nice bijective relation to tree-like structures. That can be also used here. But if we are interested in the number of, say, pattern count, then we cannot, we can only get the simplest pattern, namely the number of faces of given valency, so for example, a number of triangles. But in a quite general context, here we assume that we have an arbitrary set omega, and we only assume that our face valencies are contained in omega. For example, if omega are the even numbers, then we have bipartite maps. So if we have only the prime numbers, this is a very strange set of maps. Or we have just 4, then there are quadrangulations, which is more natural. But for any subset, really any subset, you get a central limit theorem for the number of faces of valency R. And you also get this universal sub-exponential growth rate, n to minus 5/2. The constant 12 for omega, when omega is the whole set of natural numbers, is replaced by a different positive number gamma, depending on this set omega. So what is this bijection that is used? So these tree-like structures. In this context, there are several bijections, and the bijection that we have been using is that to so-called mobiles. But what are mobiles? Mobiles are trees. So this looks strange. This doesn't look like a tree. But if you look at it carefully, it's really a tree. You will see in a moment why I painted it in that way. So what is a mobile? A mobile is a tree with two different kind of vertices, black and white. There are no adjacent white ones. And the black ones have additional, say, half edges. And it's planar. So if this half edge is on the other side, it's a different mobile. And the degree of a black vertex is the number of half edges. So the degree of this black vertex is 3. And the point is, well, you can also root it, of course. Then you have a rooted tree, yeah. So this is then it's clear. And there is a bijection between planar maps and mobiles. So there's a long text on that, and you see there are many people that should be mentioned in this context. I don't go through all of that. But the point is that there is a bijection between planar maps and these mobiles. And now you see why I've drawn this mobile in this way. And I will not go through all the details here, how you get the mobile from the Mac back and forth. But there is a quite natural method doing this, but you need some additional vertex that you choose, and from this vertex you take the distances, and there are there are pairs of vertices that have the same distance to this specific vertex. Then you see there's no arrow, the arrows are going away from this vertex, and depending of if an edge has this has an arrow or not, then you choose two different ways of seeing, and then you remove the original edges from the map and so on, and what you get is finally a mobile and back. And and of course there is also a rooted version of that, so you have a root and a specific vertex. And for example, the degree distribution is the same. So the faces of the original map correspond to the vertices, to the black vertex of the mobile, and the valency of this face, so here you have valency 3, is now the degree of this vertex, and so on. And the point is that these mobiles are easy to count because they are trees. So this is and trees. Maybe I'll go to this page. So trees have is clearly a recursive structure. So here to the root, and then you have a black vertex, and then there is again a white vertex, and everything what is here is again a mobile, and so on. So you have a mobile. And this recursive relation just rephrases into a functional equation. So it's now, you see you have a functional equation and you get a central limit theorem. So there are some details. Of course, this is, here I only consider the bipartite case. So bipartite means that black and white vertices are alternately in a row, but in general, it might happen that two black vertices are also adjacent, and the situation is slightly more involved. You get a system of equations, but a system of equations is of the similar shape as one equation. You can handle these systems of equations. And you get, of course, a square root singularity. And due to this, you have this one specific vertex, you have to get rid of that. This is an integration step. You get a different kind of singularity, will be of 3/2, but 3/2 is of the same kind, more or less, than 1/2. And from this, you get this asymptotics n⁻⁵/2. And of course, you can also do it with some counting variable. If you count some vertices of degree r, then you also get the same kind of structure, and you get a quasi-power situation and the central limit theorem. So with this bijection method And using these functional equations from the mobiles, you get a center limit theorem, and this is quite universal. There are some drawbacks, of course. You only can do phases, so phase valencies. One problem is that here, for example, these two phases are adjacent, but the corresponding vertices here on the mobile are not adjacent. So you cannot handle more complicated patterns with this method. And there's another drawback that you cannot handle, for example, two connected planar graphs or planar maps or three connected planar maps, because there is no bijection to tree-like structures known at the moment. So let me explain quickly a second method that we've been using. This was actually the first paper with Costa Banogiti in 2013. This also works only for phase valencies, but we could do also two connected maps. And this method goes back to the method by Tat, this quadratic method, that I have been mentioning before. So you introduce a catalytic variable, so the valency of the outer phase. And what you want to do now is to take again away the root edge and take also care of the number of phases of valency R. And it turns out that it is possible. But before I mention that, I should maybe say that this method, this quadratic method, is where you have to bind this catalytic variable U with C. This is systemized by Busquemilou and Jean, and also reduces to a system of equations. So these functional equations also play a role in this method, but in a different, from a different point of view. And in this special case, if you use this system of equations, and if you solve them, you get the resulting equation that has been on the very first slide. And there is a key lemma saying that if you have, again, a catalytic equation with a second variable that counts whatever, then, and if you already know that if this W is set to 1, then you have this kind of singular structure of the generating function, then if you take the solution here with the W, then the kind of singularity stays the same, and only the location of the singularity moves in W, and this, so you have precisely again the quasi-power situation, because this is exactly the situation where the quasi-power situation comes up, and you get the central limit theorem. So this lemma gives the central limit theorem. You only have to check that you have this kind of relation, so that you have a catalytic equation with the additional counting variable, and it turned out that it is possible. But this only works for phase counts again. But you get this, again, by applying this lemma, you get this singular structure, and the central limit theorem follows by the quasi-power situation. I told you that it only worked for phase counts, but we tried hard to get it for complicated pattern, but the most complicated pattern that we could handle was these double triangles. And it turned out that the combinatorics, but removing the root edge and looking around what is going on, is very involved. It turned out, and in this context, it is possible to get not one equation, but a system of catalytic equations. And the combinatorics behind is quite involved. So what you're doing is you put away the root edge and you see that there are different outcomes, and then you have to find a kind of recursive description of that. And these are the cases combinatorially that have to be handled and gives back this system of equation. And finally, it was not possible to get more than this pattern. So it seems that this method of exact counting is restricted to phase counts and very simple pattern. But we could get a result, a central limit theorem, at least for these double triangles. You can do slightly more. You can also do a pattern with no self-intersection. So what is a pattern with no self-intersection? For example, this is a pattern without a self-intersection. I come back to intersections later. So you can do slightly more, but these are very specific patterns that we could handle with this method. But finally, I want to show you something on the most recent work together with Heinzel and Wormold, where we used this method of moments with these vectorial moments that I explained before. And here we use really this combinatorial interpretation, namely that we count now the number of maps of size n with r distinguished occurrences of a pattern P. And if we divide that by the total number of maps, then we get these vectorial moments. And there is a very simple idea behind, namely, well, if we distinguish an occurrence of a pattern, so suppose that we are considering this pattern. If we distinguish this occurrence, then we can remove everything inside the boundary. If we remove everything inside the boundary, we are left with an argon. In this case, it's a quadrangle. And there are only two ways of going back. So if we want to go back, then there are two ways of doing. We can put these two edges here or the other way. So there are only two ways of getting it back. And distinguishing a pattern of this size is more or less the same as distinguishing just a foregone. And what we know already is how we can count foregones. So we know this. We did this before with the quadratic method, for example. And we have the quasi-power situation. So we know that the vectorial moments behave nicely if we just consider this. And these vectorial moments are just these numbers divided by mn. So the idea behind is to trace it back to the situation where we count occurrences of faces and then put back the internal edges. It looks easier as it really is. For example, it's not difficult to getting the expected value. So what we are doing is that we consider the generating functions where we just count foregones. And then, well, we take the expected value, which means we take the derivative with respect to w and set w to 1. And u is the catalytic variable that always there is set to 1. And then there are two ways of inserting two edges. So this gives the 2 and the c square. And so the expected value of the number of patterns is just this. So the quotients of that. So it's directly related to the generating function where we count foregons with the help of this combinatorial interpretation. So we get the expected value by considering just foregons. Now the problem starts with the second moment, because for the second moment, we have to consider two occurrences. Of course, if they are apart, so there is not a big problem. We just remove the two internal edges here and there and have this term here. So we have some correcting factors, so clearly. But there are other situations, namely that this could overlap. So this pattern here, this cannot overlap. But our pattern here can overlap. And there are different structures of overlaps, and so all of them have to be considered. And so you get the second moment or the second factorial moments by considering these three terms or these three situations. And you can imagine that if you consider higher factorial moments, it gets more and more involved. But in principle, it's possible to trace it back. So we have the advantage that if we just count foregons, we have this property. And with the help of this property, we get the behavior of the factorial moments for this random variable. And we have seen that if we count foregons, we can put edges into these foregons to get back our pattern. And this also works for a more general pattern. We only have to have a simple boundary, and that's the only condition that we need. So then but there are some problems. Well, of course, you see that the overlap structure can be quite complicated. So there are so you see here or there some more complicated overlap structures. Fortunately, we only have to consider double occurrences. This means that only this kind of situations have to be considered more or less. But of course, several of them. Triple occurrences can be neglected and so on and so forth. So it simplifies. But anyway, so this is the situation that you want to count occurrences of several, here you have 10 occurrences of this pattern, some overlaps and so on, and you trace it back by putting away the internal nodes to occurrences, several occurrences. In this case, there are only 5 occurrences of some phases of valency 4 and also of 2. And then there is some combinatorics behind and so on and so forth. And by using the asymptotics that we have here, plus this combinatorial idea, it is possible to get actually all these asymptotics for the factorial moments that we are considering and to obtain the central limit theorem. And this is the final result. This is the manuscript is on the archive for some weeks now. So if we have a pattern with a simple boundary, and then the number of occurrences of this pattern in a random planar map satisfies a central limit theorem. And it seems that this can be generalized. This can be certainly generalized to two connected planar maps and to many others. But that hasn't been done yet. So it has the potential this method has the potential to solve this problem completely. But this is only one instance. So for example, for planar graphs that have been asymptotically counted for the first time by Jimenez and Magnoy some years ago, so we know many things. For example, it's known that there is a Benjamini-Schramm limit for planar graphs. So we know that the number of occurrences, the expected value is linear, but we don't know any central limit theorem. For example, it's not known if the number of vertices of degree 3 in planar graphs satisfy a central limit theorem. The only thing we know is vertices of degree 2, but this is a trivial case. But nothing is known on that. Putting it in a more general context, I suggest the following problem. Suppose that we have a random graph with a Benjamin-Schramm limit, and we consider some local functional, for example, indicator of a pattern, but it could be more general. Let's assume it only depends on the local structure, and then we just sum up. And the question is, which conditions on this Benjamin-Schramm limit, or which condition on the graph, maybe on the macroscopic behavior of the graph, has to be put to get a central limit theorem in general. So this would be the more general context. At least for planar maps, we could give a partial solution to that, but I think the problem, so it's an interesting problem in the more general context too. So thank you very much for your. There are, for example, this bijective method works we did it in our paper. You can do it, yes. So this, because the weights are just, the weights that you have here, so this goes through and, I'm sorry. So you see here all the weights. So these are the weights for so you can put, instead of variables, you can also interpret as weights for you weight it by the degrees. And under some conditions, you get also a central limit theorem for these Boltzmann models. Yeah.
Thank you. Yeah, can you talk a little bit about the hopelessness of doing stuff like this, counting, and getting a central limit in 3D, where you glue together triangles or fourgons, and you glue them together and you make 3D objects. Has there been any attempt in the literature in this direction?
Not that I know.
Okay.
Well, it's two-dimensional is still quite involved.
So there is nothing like touch formula generalized to 3D or something like this?
Not that I know.
So.
Okay. Well,
no, it's
give
just
it a
question.
try.
More questions? If there are no more questions, let's thank our speaker again. So.